Good morning, Dr. Joe.
Good morning. Oops. Hmm. Good morning. Sorry I'm late. I just dropped my son off at the airport and good morning. And he called me through Google Hangouts or something weird like that. I don't even know. And it's like, okay, is something going on with my son Robert here? I do not know. But let's see. Let's get back to business here. Um, Just got to bring up the sapling homework here quickly. I can go over some problems. And I think we're done with new material for this semester. Unless somebody really wants me. I mean, I can go into chromatography in the last couple days if any of y'all want. I was thinking of maybe at least talking about LCMS and GCMS. Does that sound okay? Or, okay, cool. All right, I'll talk about them today then. Let me do let me get the chat here. Okay, cool. So, first, let me ask a quick question about how the homework's going. Is it going okay for everybody here? Okay, good, excellent. No No problems. Okay, cool. Alrighty, so I'll go ahead and dive into new stuff then. Share my screen. Let's see. Okay, so you know, we've talked about sort of some equilibrium topics in chemistry, and we moved into spectrophotometry, right? Which is, you know, you use light to get all the information that you can. So info from light. And that's all good. There's also, you know, then we went into separations, right? Which is really, you know, use equilibrium chemistry to separate molecules. It's another equilibrium chem topic with plumbing, you know. And then the third major topic we could talk about is mass spectrometry, right? And mass spectrometry, as my friend Jim Gardner used to say, is like blowing things up and weighing the pieces. So, so this can tell you what is, you know, what masses or what mass to charge ratios are there, and to a little bit lesser degree, maybe how much, right? In the similar sense that spectrophotometry is also quant and qualitative, right? So this is qual and quant, just like spectrophotometry is also qual and quant, right? So these are detection methods, and very commonly separations and mass spec are coupled, right? Now separations in spectrophotometry are coupled in our HPLC, right? But separations in mass spec are also coupled. And the most common tool, and by far the single most powerful tool in chemistry, is called GCMS, or gas chromatography mass spectrometry. Let me just get you guys down here where I can see you. And so there's GCMS and LCMS. These are two, you know, descriptors that describe separation and mass spectrometry detection. So mass spec is interesting because it's also a separation method, because you separate in the time domain and in the space domain, and then things arrive at a detector one by one, and when they arrive, you can know their mass to charge ratio and their abundance, right? So So it's like separation detection, that type of thing. So you separate by boiling point, and then you separate by M over Z, and then you quantify the entire response, right? So there's separation, a separation, and a quantitation. And for LCMS, you basically you separate by polarity, then M over Z, and then you quantify. And so these are, they can be very nicely sensitive techniques. The mass spec part this is highly sensitive. Whenever you create an ion and you measure it as charge, generally you get a very sensitive technique. So it's it's probably pushing towards single ions, but in practical cases, you're talking about, maybe if you have 1 million ions or so, you can detect them, So that's not much stuff. If you want to, let's say if you had 1 million rhodamine molecules in a milliliter, right? Could you detect them? And so let's see, 10 to the 6th per milliliter times a mole for 10 to the 23rd. So this is going to be 23 minus 6 is equal to be 10 to the minus 17th moles per milliliter, which goes to 10 to the minus 14th moles per liter, right? So this is pretty low, but I'm saying you could detect this by MS, and you could certainly detect it by fluorescence. But by fluorescence, you'll need a laser source, and you'll need things to be a little bit optimized. But you could do this by probably do this by mass spectrometry. So this is let's see here, milli, micro, nano, pico, femto. So this is 10 to minus 15, right? Oh, this is 12. So we're talking many orders of magnitude more sensitive here. So this is the case with many sensitive analytical methods. The trick is in the sample introduction. Right? And let's talk about sample introduction here in the next foil. So sample introduction in GCMS or any MS method, right? What you need in interior of the instrument is you need gas phase ions. right? And so it's surprising how many different ways you can get analytes into a mass spec. And it was around the 2000s, people realized that you could make an electronic nose that operated in the ambient. And the trick was just to have a very tiny leak into a mass spectrometry, and the pressure would drive the molecules in, right? And then you'd have an ionization stage and then separation stages, and you could get a read on the mass to charge ratio. And there are a good number of pre-ionized species in the air. You know, we live in a very, very dilute plasma. You know, but the but notwithstanding, you can also take neutrals in and then ionize them and analyze them in plasma. And there's also an interesting way to use an electrospray or some other ambient pressure ionization technique to desorb things. So, for example, if you want to smell a flower with with an LC mass spec, or I'm sorry, just with a mass spectrometer. Sorry, not there's no LC. Just want to smell a flower with a mass spectrometer. What you do is you take there's called an ion spray, right? Which sprays just a tiny little bit of sample out, and it makes a little jet, and then as the solvent leaves the jet's charged at about minus 900 volts or so, or minus 1,000 volts or something, and it charges the particles negatively. Then as the solvent evaporates, the molecules become, the charge density on the molecules increases, and then they disperse more and more. And it makes this interesting little fountain of ions, you know? And the neutrals can kind of get lost in this. And then you can take this little fountain of ions and point it at different things. And that's called electrospray desorption ionization. So as an example here, desorption, electrospray ionization. And in DESI, you take an ESI source, and an ESI source is it's like a little metal needle. And this metal needle is held at -1 kV, right? And then you can somehow establish a little flow of droplets out of here. And what will happen is that the surface of the droplets will pick up a negative charge. And then this will cause the negative charge density on the surface plus the solvent evaporation. These two phenomena combine to create an atmosphere of highly charged ions. And it's an interesting dynamic, right? And this whole process is called electrospray ionization. And there's a fascinating story behind this. A guy named John Fenn. He recently passed away, I think. He was a Yale chemist, and he developed DESI. And he's one of the few people that can get away copyright infringement on Disney, because in his talks, he used to always use Dumbo. Dumbo was the elephant that flew with its ears. And so, well, anyway, that's how that worked, because and so he would show us a little clip from Dumbo in his talks. I thought that was kind of cool. Okay, Brandon, I knew somebody was going to ask. This is just extra info, and it won't be on the final. Well, let me ask you. Would you like a question on the final on this type of stuff, or no?
I don't think it'd be bad.
Answer in.
I just wanted to
Okay.
start consolidating what info that I need to study and what's just useful information on the side. So I wouldn't mind a question on this.
Sorry,
but obviously it's up to you.
Okay. No. I don't want it to be up to me. I want it to be up to you. I want you guys to take the blame.
It's your class. You can't just blame it on us.
No, it's our class. We have to blame it on everybody. I can't always take all the blame. There's no clear answer here, is there? Okay. So I was thinking about some real easy general questions about about mass spectrometry and how it fits into the bigger picture. But we're just now getting through electrospray ionization, right? Gosh, somehow I managed to not quite put the legs on the ends. But so electrospray ionization, that is, and then there's electron impact ionization, which is it's not used when you have solvent. This electrospray ionization is a high pressure type of thing. I mean, it's done between ambient pressure and, say, I don't know, 1 torr or so, like the first 10 to the third. Like, it's like there's between 1 bar and 1 millibar, shall we say. And then 1 millibar and 1 microbar, then you have electron impact. But they're kind of different in other ways too. So let me just electrospray ionization. This is basically how you do LCMS, right? So this is the liquid And that's how you get liquid chromatography to talk to a mass spectrometer, is you do electrospray ionization. And there's a lot of patent workarounds, and I think the patents are probably expired anyway. But it's called turbo spray, and ion spray and other things like that. Somehow they keep the spray, and it's like, okay, fine, whatever. But the idea is simply that you have this charged needle, and then obviously there's there's ground planes out here, right? But you have this flow of gas, and it's it's typically nitrogen gas flow, something like that, a drying gas, and sometimes you have countercurrents and things like that, but the but the but there's a dynamic that happens right along this droplet that comes out, and it has to do with the surface tension. So if you were a droplet of water, let's say, imagine you were a droplet of water, and your shape is a sphere, right? And you say, well, why is your shape a sphere? And I think the answer to that is there's bulk tension and there's surface tension. Hey, Robert. Robert? Hey, Robert. I think he butt dialed me.
Hello.
Hey, Robert. How are you doing, buddy?
Good. Unfortunate occurrence, though. My calling you on Google Hangouts can probably let you know what that is.
Oh, what's happening?
My phone, it's left on an Uber.
You left your phone on your Uber.
Yeah.
Oh, shit.
I didn't notice until it's already zipped off.
Oh, fart.
I know. I'm super sorry, Dad.
Well, I'll try to track it down for you, but your flight leaves in 45 minutes, right?
I know. Yeah, that's what I'm calling you.
Okay, so I'll try to find your phone then. But
You can call it and see if the guy picks up, and then tell him everything.
oh, okay, okay, alrighty, I'll do that. That's a good idea. Okay, I'll do that right now. I have a phone emergency. Did you guys catch that? He's on a plane to Medford. He left his phone on the Uber. So, man, okay, I gotta call his phone. So let's take 5. Sorry. Sorry, guys. My son has to learn what it's like to live in the Stone Age now. No phone. I just cannot believe it. Oh, I feel so bad for the poor kid.
Did you get a hold of the Uber?
Yes, the Uber driver, he called me. No, I don't know what happened. Did I call him?
I think so.
Oh, I called Robert's phone, of course, and the Uber driver picked up. And so I'll pick that up later. But now Robert he's gonna have to call me back because I don't know where he is, you know. So when he calls me back, then I'll get back to him. But for now, we can continue our talk about electrospray. But so electrospray ionization, it's a way of making an atmosphere of highly charged ions, and basically you charge a needle, and then you pump flow out of it just a little bit, and you hold the needle generally at a very negative potential. And the negative potential, oh, here he is. Here, oops. Come on, buddy. Hey, Robert. Robert?
Hello?
So my son was in a conversation with his Uber driver about early Christianity, and his Uber driver was Assyrian, which is a flavor of Christianity from the Middle East, and he speaks Aramaic, which I don't have no idea what that is. That's some old language. Anyway, so and the idea about making this aerosol of ions is that if you get the charge density high enough on the surface tension goes down, and then it becomes surface pressure, right? And it's basically, you know, if the ions have conductivity, then their charge will accumulate on their surface, right? And then as the charge density on the ion becomes larger, then the amount of surface area will want to increase, right? And so if it forms two droplets, then there's more surface area, right? So that's a downhill energy step. And so the electrospray ionization idea is simply that, you know, you can drive this by biasing your needle more and more negatively, and so for the purpose of chromatography, usually need to add formic acid or some other small, I don't know why they use formic acid. You have to add a buffer. You have to add a buffer of ions. So typically a formate buffer is added. You guys know the structure of formic acid? It is H, C, OH, CO2H, right? And it's a it's used by ants. It's the sting in red ants. And the form, it's actually a reasonably strong acid, so you get H, C, O minus, and this formate anion charges up the droplets and causes the description is called Coulomb explosion. Of the droplets. And that's just a lovely way of getting ions into a mass spectrometer, you know. So then basically you've got LC, and then you've got charged droplets, and then you've got charged molecules, and then charged molecules, they're mass analyzed. You know, they go into vacuum. They're mass analyzed and then quantified. And so the mass analysis of ions is you know, that's a whole interesting subject. You know, there's many designs of mass analyzers, and they all, you know, they all involve basically like some of them involve the that's kind of a complicated start. You know, some of them involve accelerating the ions through a potential difference up to a certain velocity, and then measuring how long it takes them to get through a drift tube, and that's called time of flight. For example, you have two plates at a fixed potential difference, and you get the ions to accelerate through those two plates, and they pick up a fixed amount of kinetic energy. It's a delta V basically, and that's equal to mv squared, or you say delta E equals mv squared, right? Half mv squared. And then so you can analyze the mass to charge ratio by the velocity. And there's lots of tricks in that area of getting a mass to charge ratio. But so for LCMS and GCMS both, LCMS, this uses electron impact. Ionization, and that's a hard ionization method. And in EI, the molecules come out as fragments. Well, let's say they're often fragmented. So you get M plus an electron makes M plus 2 electrons, right? And how does this happen? This is endothermic, right? But this is a very hot electron. Meaning it's intersecting the path of the molecules with high kinetic energy. So there's, once you have a vacuum, you can do all kinds of crazy chemistry because you have, you can react things with electrons, and you heat up the electrons by you boil them off of a tungsten filament under vacuum, and you just apply a god-awful voltage to this tungsten filament that you're heating up, and electrons just come flying off into vacuum, right? And then you just put a grid or a cup or something that's held at ground or held at some relatively positive potential. The electrons will stream from the one place in space to the others, right? If you actively pump this, right, you have a vacuum pump set up on this, and then you introduce a flow of, say, gas, a leak of gas into this, then the gas analytes will come out sort of as a sort of a spray or a jet, right? Then they'll be intercepted by these high energy electrons, and you'll be able to collect the cations from this on a different set of optics downstream. And so you can direct these guys into a mass analyzer. And this hard ionization means that you get every molecule has a predictable, library searchable set of fragments, right? So if you have, say, benzoic acid, right? First of all, what cations is it going to form? Well, you can get this is C7H6O2, right? No, yeah, O2, right? So this is going to form C7H6O2 plus, right? And that's a cation made of benzoic acid, right? Say, well, what? That doesn't make sense, right? Because all of our chemistry training tells us that benzoic acid forms the benzoate anion. And that's true in solvent. But in the gas phase, it's kind of like anything goes, because things aren't at equilibrium. Things haven't reached some sort of energy minimum. And this benzoic acid cation is it hasn't reacted with everything in its surrounding. It's basically in an expanding jet. It's been introduced into vacuum, and it's not colliding very often with other molecules. And the majority of the other molecules around are helium atoms, right? The majority of the other gas phase species are helium atoms. And so this benzoic acid cation will fly out into vacuum, right? And then you can analyze it by mass to charge. You can put it through a quadrupole or a time of flight or a cyclotron or an ion trap or an orbitrap or a magnetic sector or an electric sector or any of these other different types of mass analyzers. And you could say, oh my gosh, this has a mass to charge ratio of 1 divided by, or of this mass divided by 1, right? Or you can also get C7H6O2 2 plus, right? Or you can get C7H6O2H plus, or C7H6O2H two plus, right? So there's a lot of variety in the products you can make. So you can also make C6H5 plus, right? This is a naked benzene ring that's a cation, right? And that will definitely form, right? And then you'll also get some some CO2 plus, right? And so all of these fragments make up the spectrum of masses that you find, right? Right? And this is what, I mean, this is, can you imagine how exciting this must have been for like if Gregor Mendel or Dalton, Frank Dalton, could have seen something like this? Can you imagine how revolutionary and exciting that would have been? You know, like to see that the universe is really comprised of identical molecules, right? Like you can have two benzoic acids that are completely and absolutely identical in every way, indistinguishable, right? And that was that was kind of like one of the debates about reality, like, what are we made of? What is all this stuff, And then to see it boil down to these simple indivisible quantities, I like to make a joke about when we get fresh water out of the millipore unit or whatever over in DH10. I say that you want to make sure to get that water because the protons are fresh. And it's because protons don't have age. There's no such thing. There's no concept of old for a proton, or an electron or anything like that, So so you can take any compound and break it into a spectrum that's all its own, Every molecule will produce a unique spectrum. And that is a huge, huge advantage to the chemist, right? It's impossible to overstate how cool this is. So so if, for example, let's say you have an LCMS, right? And you've got a UV detector, right? And then you've got an MS detector on the same instrument, right? Well, you might, one thing about the MS detector on an LC is that it's going to have a constant, annoying background. Very hard to suppress. Very hard to deal with instrumentally, and very hard to deal with computationally, because it has enough variation and stuff that it's hard to get rid of. So, but let's say you have this UV trace, right? And you see this. So you have something like Diet Coke, right? Got some unretained stuff, then you've got a couple of other peaks in there, right? This is the ultraviolet. This is signal versus time. And let's say this is the summation of all the M over Z channels versus time. Like this will be what you would describe as the total ion mass spectrum. So it's basically you get all the ions, you mass analyze them, and then you throw away that information, you add it up again, right? So you kind of do a heretical thing from the analytical chemistry perspective. And so here we'll get, at each point in time, we're actually going to get a mass trace. We're going to get signal versus time, but then you can have the overall M over Z, right, which is probably going to go it might do something like this, right? It might have more structure than the UV, right? Because the ultraviolet, it's basically the UV is also throwing away information, because you're just taking, you take the absorption spectrum across a bunch of wavelengths, and then you just pick one. Say, okay, what about this wavelength, So it's just kind of a silly thing, right? But then you can take the mass spectrum, and then you can say, well, at this point in time here, you can say, oh, this guy here, this has these three masses, right? And so you've got, this is M over Z, right? This axis out here, right? And then at every point, you get a new spectrum, right? And each spectrum is unique.
You've got to move the paper up a little bit.
Sorry. I was doing all that artwork. This is a fun class because I get to do artwork. Even though it's bad, I know it's bad. Right? And so you have two separation channels on this LCMS, right? You've got polarity, and then you've got mass to charge. And in theory, if you had a good least squares program like we used for the Raman, you could take the superposition of all these, like you could just directly inject your analyte into the mass spectrometer, and you'd get out the superposition of all these guys, something like that, You get all the mass spec just all collapsed onto one another, and then you could analyze that and say, oh my gosh, this is the combination of this, and this, right? And that's fine, actually. If you can do that, that's awesome. It's so much faster and everything. But you have to have a library of all the mass spectra that all the molecules produce in order to do that. Does that make sense, more or less? So you might think, well, LCMS sounds like such a powerful technique. Why would anybody ever use anything else? And I kind of agree with you there. You know, like, why would LCMS be limited in any way, you know? But the problems are all practical with LCMS, right? Because LCMS is bare, right? It's just not easy. Even after, you know, like 40 years of electrospray, it's still not easy. And there's lots of things that just do not spray. I mean, you can make the molecule and you can inject it and you just see nothing. So so it's difficult. It's difficult. Some analytes don't show up. Some of them don't ionize or don't ionize easily. The electrospray units are problematic. They clog. They fail to spray. They're not easy to reproduce. They always have a large solvent background. You always need buffer, etc. Right? Still, if you can do it, it's a very powerful technique. And because if conditions are right, you see a lot, and you can identify a lot of what you see. So let's have a pharmaceutical Gedanken experiment here, right? You're working in a pharmaceutical place, and the organic chemists have produced a product, right? And they give it to you as an analytical chemist, right? So you have and you're asked, well, what is it? And is it pure? And how much is it there? Right? Well, in order to answer a question like this, you have to have some idea as to the volatility of your compound and the other compounds in the matrix, right? Because, you know, if somehow, you know, the molecule you're looking for looks like, say, hexadecanoic acid or something simple like that, you know, like a simple ester or alkanoic acid, or maybe a simple amine or something, and they're not too huge and they're not too high boiling, you know, then the way to do the analysis is going to be GCMS, right? The first question you ask is, can I use GCMS, right? You want to ask that question. Can I use GCMS, right? And why would you prefer GCMS to LCMS? For you know, this identification quantitation process, or just in general, why is GCMS superior to LCMS? Like if you have the same analyte, you can analyze it using the same using these two different methods. Why would GCMS 99.9% of the time just be so much better?
I think because GCMS is faster than LCMS.
Yeah, that's very possible. Yeah. It's I think overall it's very likely to be faster. It's very likely to be faster, right? So because GCMS it's basically it's wonderful because it's it's relatively fast. You know, from injection to detection, it may be similar to LCMS, but it can be faster. It's certainly going to be cheaper, right? Because an LCMS is not cheap to buy or to maintain, right? The GCMS is efficient. And I mean efficient in the separations idea. It produces 100,000 plates. (10 to the 5 to 10 to the 6 plates. Right, remember, a plate is a region of space in which the molecule can come to equilibrium in the column. So in its transit through a GC column, an average molecule may interact with and partition into the stationary phase 1,000,000 times. So you're going to average over 1,000,000 of these types of interactions. On an LC column, it might be closer to 10,000. So for GC, the peaks are much narrower. They're much more well separated. So what might look like one peak on an LC might resolve into 2 or 3 peaks on a GC, right? Let's say if you had one octenoic acid, or omega octenoic acid, right? If you had other structural isomers of that, where it's like 16 octenoic acid, 15 octenoic acid, 14 octenoic acid, then on an LC, they would just all coelute. But on a GC, you could probably separate them. you'd see a separate peak for each of those structural isomers, you know? And then you could get their charge to mass ratio, blow them up, weigh the pieces, and then it's very likely that they would have unique mass spectra. Cindy, describe your background.
That is the Old Globe Theater in San Diego, as viewed from the balcony at the California Tower of the Museum of Man.
No kidding. Wow. That is cool. Isn't that cool? It makes you want to visit San Diego. I remember, yeah, I know. It's been a while since I've been down there. I'm a particular fan of La Jolla. And I mean, it's just like there's just a few shops out there and things. It's just kind of peaceful. But so that's so cool. Thank you, Cindy. Everybody's so bored with me, right? But so if you can't use, but let's say that you have a larger molecule or a molecule that has, it's so polar or something that it doesn't, you can't get it into the gas phase, right? You just can't quite, it just doesn't come out of the GCMS. So for example, when you do GCMS, you have to inject, you have to dissolve your sample into a volatile solvent and inject it, you know? So like you might need ether or dichloromethane or something like that, a low boiling solvent that boils easily, yeah? There's a low enthalpy of vaporization. And so if the molecule you're working on just doesn't do that, you know, and there's a large number of molecules that won't do that, then you may be relegated to LCMS, right? So if you can't do GC, if you can't do this fast, cheap, efficient, and good MS interface, then you can use LCMS, right? And you throw away a lot of plates and a lot of convenience and a lot of certainty about what you about the chemistry of what's happening. But you can see a much larger number of total molecules, right? Can kind of see more molecules, but at lower resolution, you know? So, and you may not have a library. So, I mean, in drug discovery, you're probably not going to have a library either, you know, because those molecules are, you know, drug candidates, you know, normally they're synthesized for the first time or something, you know, so you don't necessarily know what they're going to be, but what their mass spectrum will look like. But you can work it out. you could say, oh, you can rationalize it, especially if you have the parent ion, or not the parent, but the molecular ion, which is the unfragmented, singly charged parent ion. And in that case, a lot of times you can find them. So, all right, guys. That's actually makes a pretty decent point to stop today. I know it's been a lot of yak, but I hope that when you set foot into an environment where you have to approach an analytical problem, you can choose between LCMS and GCMS and understand what they'll tell you a little bit better. All right, am I forgiven? More or less? All righty, guys. I will see you all on Tuesday, and the final is coming into view. It looks like it is going to be done on sapling. So get ready for that. Oh my goodness.